I don't see it anymore. I don't see anymore on the screen. Are you?
Please start with a welcome.
You are on YouTube.
Welcome to the 2020 EMS Award Ceremony for the Silver Medal and Young Scientist Award. My name is Velle Toll and I'm the president of the European Meteorological Society. EMS is strongly supporting the advancement of meteorology and related sciences in Europe. As such, we acknowledge excellent examples of research and operational applications, as well as the outreach and communications on our science field. Today, we celebrate the recipients of the Silver Medal and the Young Scientist Award given in 2020. Because of the COVID pandemic, no physical meeting could be held, as you know. You will be introduced shortly to the recipients, and 2 presentations will be given this afternoon, including possibilities for feedback with your presentations. Enjoy the meeting.
Ladies and gentlemen, good afternoon. My name is Tanja Cignar, and I have a pleasure to moderate this awards ceremony 2020. Let me first outline the event, how we will proceed. We will have a chair of the awards committee, Mojca Dolinar, to give a citation and laudation for the Young Scientist Award. After, I will welcome the recipient of this award, Velle Toll, and then he will present his presentation on the awarded paper. After that, all of you will have a chance to interact with our awardee. You can put your questions in the chat box, and Dominic Marbuti, Vice Chair of the EMS, he will collect your questions and read them to the awardee. After that, we will pass to Silver Medal. We will show you a short video to introduce who the awardee is, what is his contribution to climate science, and also to advocacy of necessity of action on climate change. I will exchange a couple of questions with the awardee, and then he will present his presentation on our climate from past to future. Also for the awardee, the Silver Medal awardee, you will have a chance to ask questions. Again, you will have a chance to put your questions in the chat box, and Dominic Marbuti will collect your questions and share them with the awardee. So let's us proceed with the first thing on our agenda. It is the laudation and citation. It will be presented by Mojca Dolinar, Chair of the Awards Committee. So, Mojca, please, the floor is yours.
The 2020 EMS Young Scientist Award goes to Velle Toll, young scientist from Estonia. He has been recognized as an exceptional young scientist based on his publication in Nature 2019 with the title Weak Average Liquid Cloud Water Response to Anthropogenic Aerosols. His contribution in Nature is really something that makes a difference, because although the physical processes of aerosols feedbacks in climate systems are quite well recognized, the scale of aerosol impacts is a topic that is still debated. And in this sense, Velle's work is an important stone in the mosaic of understanding the interactions between cloud and climate. And what is more, this finding has a direct implication. Namely, it reduces the uncertainty in projections of future climate. But not only the results of the published paper, also the approach of this group is a novel. They used MODIS satellite data to analyze the properties of polluted clouds downwind of variety of anthropogenic air pollution sources. And the third thing that convinced us about Velle's exceptionality is that although he's a young researcher at the very beginning of his career, this awarded paper is not an exception. He's been the leading author of many high-profile papers so far. And in this early stage of career, he already achieved many important academic steps. So, dear Velle, congratulations in the name of the whole award committee. And keep on the path of research with such a zeal and excellency you have shown so far.
Thank you, Mojca, and welcome, Velle. We are glad that you are here today with us, and of course, we wish you all the best for your career. Congratulations for this excellent paper, and now you are ready to give a presentation on this topic.
Thank you.
So please, the floor is yours. You can start with your presentation.
First of all, big thank you to European Meteorological Society for the Young Scientist Award. And thank you to Estonian Meteorological Society for nominating me. Also, I would like to thank all the co-authors of this work, especially Nicolas Belouis from University of Reading. The title of my presentation today is Anthropogenic Aerosol Impacts on Clouds and Earth's Climate. One day, 4 years ago, I was studying the impact of shipping emissions and volcanic emissions on clouds. I was asking myself a question that why I don't see such polluted cloud tracks over land. I realized that such true color satellite images, what are similar to what we see with our own eyes, are not optimal. So I need to use satellite measurements what are sensitive to cloud droplet size. And a few hours later, I had found many hundreds of such land-based industrial polluted cloud tracks. And I immediately realized that these polluted cloud tracks will help to better understand anthropogenic impacts on Earth's climate. What are aerosols? Aerosols are tiny solid and liquid air pollution particles that are harmful to human health, but offset part of the greenhouse gas warming. And one of the main sources of anthropogenic aerosols is burning of fossil fuels. Aerosols interact with electromagnetic radiation directly. So here you can see wildfire smoke, and the smoke is bright compared to the underlying dark ocean. This is because smoke particles reflect solar radiation back to space. In addition, aerosol particles are necessary for cloud formation. And now if we add anthropogenic aerosols into atmosphere, the cloud water redistributes over a larger number of cloud droplets and clouds become brighter, Here you can see clouds impacted by shipping emissions as these bright lines. And my research is really about how much brighter do clouds become in response to anthropogenic air pollution particles. Here you can see effective radiative forcing of Earth's climate. So radiative forcing in watts per square meter measures the difference between energy received by the climate system from the sun and energy given away by the climate system as thermal radiation to space. And now if Earth receives more energy than it gives away, the forcing is positive and Earth warms up. The total anthropogenic forcing is the sum of greenhouse gas warming here in red and aerosol cooling here in blue. The probability density function of greenhouse gas warming effect is rather narrow, meaning that greenhouse gas warming effect is very well quantified. But there's rather large uncertainty in the aerosol cooling effect, and really the aerosol cooling effect dominates the total uncertainty in the anthropogenic radiative forcing. If there's very strong aerosol cooling effect on the Earth's climate, here the temperature projection with the red line, then rapid future warming is expected, as this would mean that already observed warming is caused by a relatively weak positive forcing. And when there's no aerosol cooling effect on climate, here the temperature projection with the blue line, then much more moderate future warming is expected, as this would mean that already observed warming is caused by relatively strong positive forcing, and our climate is not that sensitive to anthropogenic forcing. So this here illustrates why it is very important to better quantify aerosol impacts on Earth's climate to more reliably predict the future climate. The main aim of my research is to better quantify the anthropogenic aerosol impacts on clouds. The question to you with this true-color MODIS satellite image is that, do you notice brighter aerosol polluted cloud tracks here in this image? I assume the answer is no. Here you can see a similar MODIS satellite image, but here near-infrared channel is also used, what is sensitive to the size of cloud droplets. So this whitish line here is polluted cloud, and it has been polluted by aerosols originating from this industrial pollution hotspot here. And why these polluted cloud lines are super nice is because we can directly compare the properties of the polluted cloud to the properties of nearby unpolluted cloud here in brownish, yellowish colors. And this provides a means to give confident answers to questions like how much brighter do clouds become due to anthropogenic aerosols. Here's another example of polluted clouds. Here's Shanghai region in China, and here are polluted clouds over ocean. So these brighter clouds here have been polluted by aerosols originating from the Shanghai region. This is the main scientific finding thus far using polluted cloud tracks. As expected, the cloud droplets are smaller in polluted cloud tracks compared to the nearby unpolluted clouds. However, in contrast to what is assumed in many climate models, clouds are not thicker in response to anthropogenic aerosols on average. So on average, the thickness of clouds is rather similar between the polluted and unpolluted clouds. In summary, there's still a lot to discover using polluted cloud tracks. Thank you.
Thank you, Velle. Excellent, and congratulations again. And now I'm handing over to Dominic Marbuti to handle the questions collected in the chat box. Dominic?
Dominique, you have to unmute yourself.
It is unmuted. It's fine. Okay, Velle, first question to you then. How would you plan to continue the present research which you have started? What are your plans for the future now?
Thank you. So at the moment, I have a research grant funded by Estonia Research Council on this topic. And at the moment, we have mostly looked at do clouds become thicker or thinner in response to air pollution. But in the future, I would like to study also that how many clouds do we have in more or less in response to anthropogenic aerosols. So I'm hoping to extend that research and apply for next proposal grants on similar topics. So definitely want to continue on aerosol cloud interactions because it's a very important aspect in regards of uncertainty in future climate projections.
Okay, second question then. As we are all affected by the current COVID-19 pandemic, even if there is some improvement in most of Europe, how did you have the opportunity to see whether the forced confinement has improved air quality in many places? So what are and what would be the resulting climate impact from your side?
Yeah, excellent question. So the climate impacts actually are rather weak, but nevertheless, the emission reductions provide a means to reduce the uncertainty in our understanding. So it will give new insights, and many people have already studied different physical processes. And also I have looked into aerosol cloud interactions, that how have impacts on clouds change due to emission reductions. So it's a very nice research material.
Okay, thank you very much. And I will hand over to you, Tanya.
Thank you, Dominic, and thank you, Velle, for this nice presentation and also answering the questions from the floor, actually from the chat box this time. And now we will move to Silver Medal. And I'm saying hello to Jean Jouzel. Hello, how are you?
Thank you, Tanya. I'm going well in Paris, and thanks for this organizing this ceremony of the European Meteorological Society. Thanks to all of you.
Well, it is great to have you with us. And first of all, I suggest that we all watch a short video compilation about your awards and about your achievements. It is really impressive what you did in your career. So please, can we start with the video? Jean Jouzel, what can I say? Your achievements are really impressive. May I ask you a little bit personal question? If you would have a chance to rewind time at the beginning of your career, would you take another path, another topic, or you would stay with the one you did?
Yes, I think I will keep. Thank you, Tanya. I will keep the one I did. I did it by chance because I was proposed this PhD on water isotopes, and it's only a few years after that I really moved towards the climate issue. This was in the 70s, and we were not really yet discussing of climate change issue, but indeed it was I was very lucky, I think, to be at this link between past climate change, which is my field of expertise, and future climate change. And this is really very interesting because it's open also, obviously, it's a field of research which is very open toward general public, to work policy making, policymakers. And so I think I have been very interested by this type of research, and I am fully satisfied. And I was not anticipating when I was young scientist in the 70s, 60s, and the 60s that I would have such recognition as today, because this is really marvelous. Thank you. So I will keep it.
And among so many achievements, so many important events in your career, according to your perception, which one is the most important?
I think the most important is this finding of a link between greenhouse gases and climate in the past. This was a discovery with colleagues from Grenoble in France, from Soviet Union, from Leningrad, Moscow at that time. And thanks to the Vostok drilling in Antarctica, we were able to show this link between, with my colleagues, Dominique Reynaud, Jean-Marc Barnola, for example, we were able to show this link between greenhouse gases, which were less concentrated for CO2, for example, during the last glacial period than today, and to show also that over the last climate cycle, at that time, there was no value as high as we were already. The value of we were practically over 2080 ppm at this time, and this was never encountered during the last glacial age. So this was really the proof that one of the strong indication of the fact that human activity were at the origin of the greenhouse gas concentration, and this was very important at that time.
Thank you for answering this question. I think that all your achievements are very important. And I have learned that you have prepared for us a presentation on climate from past to future. And now we are all excited to hear what you have prepared for us in this presentation. So the floor is yours for the presentation.
Yes, thank you. And again, I would like to thank I would like to thank the European Meteorological Society for this award, and I am very proud of, and also the award committee, obviously. So my scientific activity over the last 50 years, slightly more, I started my PhD thesis in 68, has been really organized around the powerful tool, which is a distribution of water isotopes in water vapor and precipitation. And I will focus on solid precipitation. So this tool was very important all along my career. It's still unvaluable archives, Antarctic and Greenland ice core. So I mean, I was lucky to have access through large collaboration in France, European level, also with other colleagues around the world to have access in our laboratory in Saclay to Antarctic and Greenland ice core samples. And my interest was really, this gives a valuable archive of past climate change, but my interest was in this information, what is really relevant to the future of our climate. This has been my I'm sorry, so I go too fast. So I start. My first, the property I am interested in, I'm sorry if I can come back, but it's go too fast. Can I come back to the second slide, if it's possible? Yes, the second one. Yes, the previous one. Thank you. So I am sorry. I'm sorry. So water isotopes. So you know, water is H2O, but we have also isotopic molecules, oxygen 18, oxygen 17, and for hydrogen we have a stable isotope, which is H2, deuterium for us, and tritium. So this molecule, this gives. We have a lot of different water molecules with different isotopes and which has different properties, in particular saturation vapor pressure and diffusivity in air. So, as a consequence of this difference in physical properties, at each phase change, the liquid and solid phase are enriched in EV isotopes, and as a consequence, in a closed system, the vapor phase is depleted in those EV isotopes. So as a result, it was very simple. The isotopic concentration of liquid precipitation decrease with temperature of formation of this precipitation. So my first so during my PhD thesis, I applied this tool to large hailstones. This large hailstone were really 6 to 8 centimeter diameter, and we were able, through analyzing this distribution of water isotope in this hailstone, to reconstruct the trajectory of hailstone in cumulo during their formation, with ascents and descents. And if you have such a large hailstone, you have to have to be able to keep this hailstone in the cloud during more than 20 minutes. I was also interested in, at that time, by not only by the modeling, how do we relate the isotopic content of precipitation and of water vapor in a cloud to climate parameters, and this was the main topic of my work in the 70s. And I was also interested by, so you see such an example showing that the gradient of deuterium of water isotopes is depending of temperature of altitude and temperature in the cloud. So I continue to develop isotopic model, which was necessary, but no, not only. So I was looking then to Antarctic snow for Greenland and Antarctica, when it was well documented, showing also a decrease of the isotopic composition with lower temperature when you go from the coast to the central part of Antarctica. This was well documented, and thanks to, for example, taking into account what we call the kinetic effect at fractionation, we were able to show that a simple model really well account for this relationship between temperature and the isotopic content of snow and the temperature of formation. This was, sorry, it's long. Yes, this was indeed, my interest was not, this was motivated by deep drilling of ice core, which were started in Antarctica at that time. The first ice core in Antarctica, which was drilled, was at Bird by Danish and American colleague, and in the 70s, thanks to my colleague Claude Lorius, which was really very active in this field, I was associated to the first French ice core, Domsey, which was covering 40,000 years. But more importantly, the most important result came in the 80s, thanks, I cited this, to the Vostok ice core drilled by Soviet scientists. So what we did, we were lucky at that time to have an ice core which was covering it was more than 2 kilometers long. You see that here, the last 2.5 kilometers of this drilling. And so we were analyzing in our laboratory the deuterium content of this ice core. And you see really here, when you have a lower deuterium, lower isotopic concentration, you really have colder temperature, and you see very well depicted the last glacial maximum, the current period, the Holocene, the last glacial maximum of the previous interglacial on the previous glacial period around 150K. So this was very important, so this result was interesting for a first aspect. So it was really illustrating the link confirming the link between variation at that time scale, climate variation, and insolation change. This is known as the astronomical theory of the Ice Age. And we see really well here the imprint of the 40K cycle, which is obliquity, on the 20-year cycle also, which governs the insolation in June at 65 degrees north. You see very well this imprint of insolation. This was only a confirmation, because this link between insolation change and climate was really demonstrated by a deep sea core 10 years earlier, during the 70s, by John Imbrie in particular. But the main result of this Vostok study was it was important to have access to climate, but it was thanks to my colleague of Grenoble, Jean-Marc Barnola, Dominique Reynaud, Jérôme Chaplas, they extracted the air bubble from this ice core, and they were able to provide quantitative reconstruction of the composition of the air bubbles. So it was the first time that the variation of the composition of the air was reconstructed. And so you see, the most important result from this study was this, I already mentioned, this really close link between what we reconstruct from isotopic studies, temperature at Vostok site, and CO2 and methane concentration. And we had a lot of a series of articles at the end in the 80s and the beginning of the 90s, which were very important, very well cited still. And what this illustrates, so again, so it was a confirmation of the role of insolation change, but it illustrates a link between climate and greenhouse gases, and our interpretation, which is still valid, that greenhouse gases, I mean, the pacemaker of the Ice Age is really insolation change, but greenhouse gases have acted as amplifier of this initial climate change due to insolation change. This is a current explanation and still valid. We extended. So sorry. We extended this record to the last 400,000 years, and indeed still demonstrating, really confirming this link between greenhouse gases and climate over the last 400,000 years, and also showing that during this period, the value, the maximum value are never over 300 ppm in CO2, which means that the more recent value are really very different, not far no, over 400 ppm no. So I was also lucky at that time to be associated with research in Greenland. And so in central Greenland, this grip and gives 2 ice core, again, it was a 3-kilometer core in central Greenland. And here, the main result obtained through this cores was to really show that we can have very rapid change. When you see during this the last climatic cycle, it's very different from what we see in Antarctica. It's really very rapid change, what we call Dansgaard-Oeschger events, and with large temperature change up to 16 degrees C in a few decades. And this obviously raised the question of climatic surprise. This was a very important result with respect to future climate change and this notion of climatic surprise. And I was also at that time interested by, continue to be interested by modeling. In particular, I focused on the use of not only of one isotope, but combination of 2 isotopic species, deuterium and oxygen-18, through the deuterium excess. And indeed, the deuterium excess in ice core provides information on the condition, temperature, relative humidity prevailing at the origin of the precipitation. In short, we can have information of what is occurring in the ocean, over the ocean, through ice core, from studying ice core. And I still continue to be interested in water isotope modeling. We pioneered with the first paper on the introduction of water isotopes in general circulation model, was published in 83 with my colleagues. We pioneered this work with my colleague Jean Jouzel, and I am still very interested by implementation of water isotopes in a general circulation model, which are obviously of common use for meteorologists and climatologists, but in our case, it gives really information about the distribution of water isotopes. And what I show on the right is the fact that when we compare the prediction of this model, this was published 3 years ago, and the distribution of, on the observed distribution of water isotopes in Antarctica, it fits really well. So the last, we started so the Vostok ice core was reaching 400,000 years, and thanks to a European project, again, to the Domsee site, I was in charge of this project in the 90s. This European project for ice coring in Antarctica, you see an ice core, allowed us to extend this record to the last 800,000 years, and to indeed confirm this strong relationship between temperature in Antarctica and isotopy on CO2 and methane concentration. And also what was very noticeable is this long interglacial 400,000 years ago, which lasted 25,000 years. And the reason is that at that time, the orbit of the Earth around the Sun is quite circular. And in this case, entering in the next glacial, in the following glacial period, is very slow. And it's very fortunate for us that we are in the same situation, in a similar situation. Indeed, the last 4 interglacial period have lasted not more than 10,000 years, and you have to go back to 400,000 years ago to see a long interglacial, more than 25,000 years, and we are in such a situation. So this means that without intervention of human activity, we would have a very long interglacial, more, I mean, probably 15,000 year additional duration of this of our interglacial. So to sum up, so what I was interested in is the relevance of paleodata to future climate change. So this relevance is illustrated by, I would say, the main point of this work, of this more than 50 years of work, of this link between greenhouse gases and the Antarctic climate. This allows to, and we attribute this, I mean, it is this amplification of insolation change, which are at the origin of the glacial interglacial cycle. This gives access to a way to estimate climate sensitivity with a key parameter for future climate change. I think the length of our current interglacial, it was also a key question because, for example, during the 70s, there was some people, we had already a 10,000 year duration for our current interglacial, and some people, some scientists were pointing out to the proximity of the next glacial period. So we were going rapidly from their study, we were probably going rapidly in the next interglacial, which is not true at all. Rapid climate change was also a topic I am interested, and it's also obviously directly linked to future climate change because this notion of climatic surprise. From my scores on other studies, we can also look at climate variability at various timescales, the last millennium or more the Holocene period. And what is very important, but not only from deep ice core, but also from other archives as deep sea core, is all the information we get on sea level change. For example, this key question of the last interglacial, this period was only probably 1 degree C warmer than today, something like this. And despite this very limited warming, the sea level rise was at least 6 meters with respect to today. So this really raised question about the long-term change in sea level change, due in particular to the behavior of the Greenland and the Antarctic ice cap. Though I will, so it is really with this relevance of paleodata to future climate change, which has motivated my interest for future climate change. I have been very interested in future climate change, its consequences on the related issue. I mean, I am also very interested by future climate change, but I would say my main contribution to our field of research is really about paleodata and largely based on ice core today. And I would like to thank all my colleagues of this very active community, ice core community, which has provided and is still provided. The hope now is to go beyond 1 million years to get a new core, which provide information which are really very, for me, directly relevant to future climate change. Thank you.
Thank you very much, Jean Jouzel, for this very informative presentation. And also, again, congratulations for Silver Medal. And now I'm handing over to Dominique Marbuti. I know that there are already several questions in the chat box. So, Dominique, the floor is yours.
Thank you, Tanya. Jean, I would start with a question, by the way, from our Young Scientist Awardee, Velle, and I think as a former chair of the IPCC Working Group 1, you are probably well placed to have an answer to that one. And this question is, how does the climate sensitivity derived from ice core data compared to the IPCC AR5 central estimates?
It compares very well. For example, we published in 90, in this paper I cited with Claude Lorius, an estimate of climate sensitivity from paleodata as being 3 degrees plus of 1 degree C. So the C degree C was what we infer from paleo data, and it has been largely confirmed, and this is currently used, this estimate of climate sensitivity from paleo data, to complement what is obtained from directly from climate models, and indeed to confirm this now in the IPCC report is it's a slight improvement with respect to the Charney report. The Charney report, it was between 1.5 and 4.5 for climate sensitivity, and in the fifth report, it was between 2 and 4.5 degrees C, and clearly what we inferred already in the 90s, and which was confirmed from paleo data, is well in this range and confirms the validity of this approach.
Okay, thanks. To move a little bit, I know that after your scientific career, and we have seen from the short film at the beginning, that you are now spending a lot of time to trying to or convincing, I would say, both politicians, public, etc., about the importance of climate change and how we could cope with and to reduce this climate change. And probably a lot of, let's say, participants have noticed this pictures of you with the Pope. And I know that you met the Pope together with your co-writer, Pierre Larouturou, to develop to him a proposal which you have prepared, both of you, about how to give money in some way for all this activity necessary to cope with climate change. Would you be in a position, in I would say, a few words, in some way, to explain the theory which you have developed to the Pope?
Yes, so this Climate Finance Pact was based on on an estimate of European authorities saying that to cope with the climate transition in Europe, we will need 1,000 billion euro per year to cope with this. 300 million euro additional, and the idea was this money could be available, and indeed it's it's important. For example, in France, we will need 20 billion euro in addition to what we do every year. So the idea to have additional money was really our idea in this finance pact. We were presenting rapidly this finance pact to the Pope, but on the climate issues, but he told us rapidly that he was very well aware of climate issue, and we have not to convince him at all. So this was 2 years, 1 year after Laudato Si encyclic. But the discussion, and I was also very interested because for me the main consequence of climate change is the risk of increasing inequalities. We were discussing more on societal aspect of climate change, for example, in developed countries, and this was I mean, most of our discussion were about inequality, societal aspect of climate change, and we were also obviously with Pierre Larouturou very interested in, but not on the climate issue, because the Pope says straightforward, I know what is going on about climate, I am convinced. But it was really interesting, and we spent 25 minutes discussing, and it was really very good.
Oh, okay then. And remaining on those issues, so we have seen also from all the pictures which were shown that you have met a lot of important person from the political world. Do you have the feeling from all those, I would say, contact which you have, in particular also through also advisory bodies to which you have been invited to participate? Do you have the impression that there is some real evolution, I would say, from our governments, etc., to address climate change?
Yes, there is a real evolution in the objective, in the text. For example, currently we have 130 countries or even more which are which has put in their country as an objective neutrality carbon in 2050, which is the case of Europe, for example. Europe is really aligned on this objective of neutrality carbon in 2050. In France, we have so. In US, thanks to Joe Biden, we have also this objective. And in China, it's really, it's 2060 for this objective of carbon neutrality. But this objective of carbon neutrality, which has been discussed, for example, by Valérie Masson-Delmotte, which was really active in the 1.5 record, was really put forward by our community only 3 years ago. It was adopted by most of large part of the country around the world in the text, but in the reality we are far from there. From this trajectory compatible with 1.5. When we look at the Paris Agreement, there are commitments of these countries, and to be able to cope with 1.5 issue, which would be reasonable for adaptation to climate change, we should multiply the effort of reduction of greenhouse gases emission by a factor of 5 between 2020 and 2030. So at some point in the text, it's perfect. I adhere to the objective in France of carbon neutrality. In Europe, I think we most of us are in agreement with this objective. But the point now is, are we able to really cope with this rapid decrease of our emission of climate change? This carbon-free really world is not so simple, and this is really the challenge for the coming decades. We still have a lot to understand to climate change issue, to climate change, for example, for extreme event, for the importance of such events like El Nino and so on. But there is also a lot to do in action, and we have also to adapt to climate change, as obviously, because this climate change is we cannot avoid a climate change of at least 1 degree C from now to 2050. And obviously, if we do nothing over the coming decade, it should be much higher, up to 3-4 degrees C in the second part of the century. And it's very important for young generation, and thanks to all. So to young, thanks, I congratulate for his young student, for Young Metallurgist Award. It's very important that the young generation take really over this both on research action, and it's very important to be active. And we will have in the coming months 6 IPCC report, and it will be again very important for our climate community at large.
By the way, as you mentioned him, and that would probably be a good conclusion then, he had a question for you about what are your views about what should be the next big research question to study in using the I-scores.
In using the I-score, so my colleague focused on extending the I-score. So there is a current project with a younger scientist, obviously, a European project, and also US and other countries are involved in this project to drill a core which is older than 1 million years. The point is that from a perspective of paleoclimate, we have a change of rings at 800,000 years. Before 800,000 years, the glacial period occurs every 40 years on the average, and it is only recently, more recently, over the last million years or even less, that we move from 40K, for 40,000 year cycle to 100,000 year cycle, which are no characteristic of climate change. So this is a very interesting issue, and it would be very important to have an I-score, I-score older than EPIC I-score, older than 1 million years. But there is also a lot of we can really there is a lot of on I-score study also on the shorter period, on pollution. So there is also a key studies with what is the role of really of accumulation change in the mass balance of Antarctica and Greenland. So we can learn a lot from ice core, and this is really what my colleagues are doing over, I hope, the next decade. And there is still a lot to do, both on surface, on shorter ice cores, and this long ice core would be very providential. It would be very nice to have an ice core older than 1 million years.
Thank you, Jean. Tanya,
Thank
I
you,
hand over to
David.
you. We are almost on time.
Okay. Thank you.
Thank you.
Tanya. Thank you.
Thank you, and congratulations again, Jean Jouzel, for your scientific contribution, but also for your engagement with policymakers and all the decision makers, also those at the very highest levels. Thank you very much for this. So this brings us to the end of this awards ceremony. Congratulations again to both of awardees, to Velle Toll for the Young Scientist Award 2020 and Jean Jouzel for Silver Medal. And thank you for the audience for contributing questions to our awardees. Thank you to Dominique to helping me to deal with questions. Thanks also to Moica Dolinar for her citation and laudation. And for rest of you, thank you for being with us. I hope that I will see you on the virtual platform for the EMS conference in September. And thank you very much. Hope to see you soon again, at least in September, and stay well and healthy. Bye-bye.
Bye-bye.